After watching this video, students are going to be able to calculate ideal gas law problems and solve for any of the variables found in the ideal gas law equation. So you can go ahead and see here that we have the ideal gas law equation with its variables. We have pressure, okay, we have volume, we have temperature, okay, so very typical units that we've seen so far. However, we also have moles, okay, which represents the quantity of the substance we're looking at, and we have a new value, the constant, or the universal gas constant here, which corresponds to 0.0821 liter ATM per mole Kelvin. This constant can be presented with different unit values, specifically usually different pressure values, but one of the most common ways is the way that you see here. And so that's the one that I'm going to require you all to memorize. Okay, so now that we're familiar with the components of the ideal gas law equation, let's go ahead and apply some problems. So in this problem here, they've asked us to calculate the pressure in atmospheres of 0.412 moles of helium at 16 degrees C and 3.25 liters. This problem, just like any of the other gas law problems we've done so far, is going to first be carried out by writing out our variables, right? Okay, so we have pressure that we're trying to solve for. We've been given our number of moles of our helium. Please make sure that you are writing out what the units are as well as what the substance is. Okay, we've been given a temperature value, 16 degrees C, and we've been provided a volume value of 3.25 liters. Okay, so now that we've written out all of our variables, what I want you to notice is that we only have one volume, one temperature. We're solving for one pressure. So unlike the other equations for gas law problems that we've done so far, where there's been, two of most of the variables, we only have one of each. So that's going to imply to me that we're going to need the ideal gas law equation. Okay, obviously the presence of moles is also a good indicator, but you need to make sure that you're connecting that even when you're not given moles. You might be being asked to solve for moles. So in this context, again, we're going to be solving for the variable we're looking for in the equation. So P is what we want. So we're going to manipulate this equation. Okay, now in our previous gas law problems, we made sure that our units match, right? So like pressures are at the same, are in the same type of unit, temperatures, volumes, what have you. Now, in the context of the ideal gas law problems, we need to make sure that all of our variables match the units in our gas constant. So 0.0821 liter ATM per mole Kelvin are the units. So all of the units of our provided values must match, okay? So volumes, the volume we've been provided is in liters, that matches our constant, okay? We're in moles, that matches the constant. Our temperature here, though, doesn't match. What that means is we're going to need to add our 273.15, and that's going to give us our temperature in Kelvin, which is going to be 289.15. Okay, and now all of our units match the constant, and we can subsequently plug our quantities into our manipulated equation. So now that we've plugged our quantities into our equation, we can go ahead and calculate our pressure. Okay, and that's going to be 3.0094. Okay, our significant figures are going to be dictated by the values we've been provided. Okay, so we have 3 here, we're going to have 3 here, and 3 here. 3 significant figures is what we're going to end up with. So 3.01 is what we're going to end up with in our value. Okay, our final value. Our moles and our moles cancel. Our Kelvin and our Kelvin cancel. Our liters and our liters cancel. And ATM is what we're going to end up with for our pressure value of the helium at that temperature and volume. Okay, so when you're calculating these problems, guys, you need to make sure that, first of all, obviously you're writing out your equation, you're manipulating the variables, that you're making sure that the variables match the constant value, and that you obviously round and solve for the correct units. We're going to look here at another ideal gas law problem. This one has a few more conversions that are going to be necessary and will be very common. Okay, so we're going to write out our variables, okay, and fill in the information, of course, that we have. We've been provided a 104.5 kPa as our pressure. They're wanting us to solve for our volume, okay? Now, in this problem, they haven't given us a number of moles, but they have given us a gram quantity, a mass quantity, and the identity of that substance. So we're going to be able to utilize that in order to figure out our number of moles, and we'll come back to that here in a second. We've also been given our temperature. Okay, so this is still going to be a PV equals nRT problem. Okay, we're going to be solving for volume in this case. Now, just like we previously talked about, all of our units need to match up with the constant. And we know that our constant is in liters ATM per mole Kelvin. And so we need to have those corresponding values. We're going to definitely have to do some conversions to our pressure. Our grams need to be converted into moles, and our temperature needs to be put into Kelvin. So we're going to go ahead and set up those conversions. So as with any pressure conversions, we use the interrelationships. That's going to give us 1.0313, okay, with our fourth significant digit there. Okay, our 85 grams is going to be converted to mole using the mole kingdom. Okay, and that's going to give us our 2.656. Okay, with 2 sig figs, right, moles of O2. Okay, and our temperature conversion is going to give us 298.15 Kelvin. Okay, and that's going to give us our values that we're going to go ahead and plug into our equation here to the right. Now that we have all these values plugged in, we plug them into our calculator. Okay, and that's going to give us 63.0406. And then significant figures, it looks like we're going to end up with 2. Okay, so that's going to give us 63 as our numerical portion of our answer. Okay, our moles and our moles cancel, Kelvin and Kelvin cancel, ATM and ATM cancel. Liters is what we are left with. Okay, and so the volume of these 85 grams of O2 is going to correspond to 63 liters. So as you guys can see, write out your variables, make sure everything matches the ideal gas constant, plug them in, check your units, and go from there.